Hello, good people. This is video number one of part two of the first two sections of Unit 6. We previously were noticing that when we're taking the definite integral or finding the area under a curve that's actually a curve and not geometrically solvable, I guess, we can approximate using rectangles. And we can use left rectangles, right rectangles, midpoint rectangles. And we're going to continue to practice that idea over and over again. But another shape that we could use is the trapezoid. And we mentioned it in the original video to start off that there were different ways to approximate. So we're going to do a little bit more work with trapezoidal approximations. And I wanted to remind you the formula for the area of a trapezoid. Here is the formula that I've been using. And I did mention, but I didn't write, and so I'm going to ask you to write it here. Some people, instead of remembering this formula, they remember it as a trapezoid has two bases that are not the same length, right? And so the way they picture it is you take the average of the bases, so add them and divide by 2, times the height, right? Because that's usually how we find the area of a quadrilateral is we multiply base times height. Well, this one has two bases that are not the same length, so we're going to average that and multiply by height. So it doesn't matter whether you remember it this way or whether you remember it this way, but just you're going to have to start to remember area of trapezoid. And you're going to find that when we look at some AP release problems, they're specifically going to say, find the trapezoidal approximation versus find a left Riemann or a right Riemann or a midpoint Riemann approximation, which means we're going to use rectangles. So if you look at the picture, our trapezoid, if you normally think of a trapezoid like this or like this would be base 1 and this would be base 2, this would be base 1 and this would be base 2. If you normally think of the trapezoids this way, then when we draw the trapezoids in the graph, they're actually shifted or rotated, right? And they're 90 degree with a 90-degree rotation. And so the height is really this delta x, the width, what we call the width of the rectangle. This would be the height of the trapezoid. And then the bases are really just the function values, right? F1 and F2, or f of x1 and f of x2. And so we're looking for the heights as the bases, and then the bottom delta x or width would be the height. And so I say that because as we look at the first example here, we're not given a graph, we're given a bunch of information in a table, but we can certainly interpret that thinking about what axis is which. Okay, so an amusement park opens its doors at 9 a.m. The rate that people enter the park at time t is modeled by the function p prime of t in thousands of people per hour. Selected values of p prime are given in the table above. So even though there is not a graph given, we could picture the fact that I have a vertical and horizontal axis. The horizontal axis, my independent variable is t in hours, and my vertical axis, my dependent variable, is p prime in thousands of people per hour. That thousands of people is important. So when we find the area, we're going to multiply this times this, because that's how we find area, right? Length times width, or in this case, finding the area, two-dimensional space. So we're going to multiply people times hours, which is going to give us thousands of people. Now, because I'm looking at it this way, or because I'm drawing this, I now see my delta x is really my height. So I need to find the delta x. Now remember, they want me to do 3 subintervals. So here's one subinterval. It has a delta t of 2. Here's another subinterval. It has a delta t of 3. And here's another interval from 9 to 7. Oh, yeah. From here to here, this would be delta t is equal to 5. And I'm stopping there. Why am I not using the 14? Because specifically they said to only worry about estimating the number of people that entered from 9 a.m., which would be time 0, to 7 p.m., which would be time 10. And so that's the only thing I need. Great. So now I'm going to apply my notation, and I'm going to say the integral from 0 to 10 of p prime of t dt is equal to, I'm going to set it up two ways so that you can see that it works both ways. So here we have 1/2 times the height. Well, the height is a delta t times base 1 plus base 2. Base 1 plus base 2. So 7 plus 11. Plus, I could also do it the other way and say, let's average the next bases. The next bases would be this times the height, which would be 3. So both of these are valid setups. You would get credit for both. It doesn't matter which one you write. Just be consistent, I guess, in your work. And then this would be, I'm going to use the original one, and then that would be 8 plus 4. So this setup is what the grader needs to see to know that, oh, you're using the trapezoidal approximation, because all of these are 3 different area setups for trapezoids. Great. We can now make it a little bit clearer here. This is going to be 18 plus, if you add these two together, you get 19 divided by 2 times 3. Ooh, 19 divided by 2 times 3. Or 19 times 1.5, I guess. Half of 19 is 9.5. So is that 28.5? I'll go back and check that. And then here I have 1/2 times 5 times 8 plus 4, that's 12. So 1/2 of 12 is 6 times 5, that's 30. So I think that one is correct. This was, what did I say it was? 19 divided by 2, so that's 19.5 times 3. I think that'll work. Yes. And so now when I add these two together, or add these 3 together, I will get 4, 6, 7. I believe that's 76.5. Again, usually these types of problems that come up in the free response section are in part 1 of the free response section, so you can use your calculator to figure that out. And you can double check it for me, and if I did something wrong, I apologize. I'm trying to finish this problem here so that it doesn't go too long. But yes, you can use your calculator to figure that out. Now, what do we find? Well, we found, remember, we were multiplying P prime times T. So we're multiplying thousands of people per hour times hours. So then what we have is that many thousands of people, period. No, there's 76.5 thousands of people, or 76,500 people, I guess would be another way to write it, with units. The full interpretation would be, this is the number of people that entered the park between 9 a.m. to 7 p.m. was 76,500 people. That's what we would have found. And that completes one example of a trapezoidal approximation. We'll do more here in the coming videos, but that's just to get us started and remembering that these formulas that are here, we need to remember and have stored in our brains.